This is my first video. I solve problems from various math Olympiads such as IMO, IMO Shortlist. This is my first video, so hopefully you like the content, and with that, let's begin. So today I'll be solving a random IMO shortlist problem. Alright, so what I'm going to do is I'm going to select a random problem using random number generator. Alright, so I'm going to be solving a problem from 2000 onwards. I don't want to solve something too old. I just want to keep it a little bit fairly recent, so it'll be from 2006 at least. Alright, so we'll be doing it from either one it represents algebra, 2 represents number theory, 3 represents combo, 4 represents geometry. Alright, so it'll be number theory, and what will the subject, and I don't want to do something too difficult. I'll be doing it from the number will be 1 to 3, so no C4s, C5s, or G1, G4s, G5s. Anyways, it'll be an N3, so 2006 N3. Alright, so 2006 N3 will be right here. Let's see. Oops, 2006 N3. Alright, looks like right there. Okay, so we define a sequence A1, A2, by that. Prove that A sub n plus 1 is greater than A sub n infinitely often. And prove that A sub n plus 1 less than A sub n infinitely often. This doesn't seem particularly difficult, unless probably missing something. Yeah. But anyways, this suggests kind of a combinatorial interpretation actually of what the quantity represents. Or actually, a construction would likely suffice for this. There's probably a construction that works. Primes seem interesting here. I'm just going to note that right now. Primes seem interesting here since they're the ones where floor of P over K will always decrease. It'll always be less than P over K. So it feels like there might be like the most decreasing for a given prime. And I'm going to try and see if that might be kind of the case. So 1 over n and I'm not going to rule out the combinatorial interpretation just yet, because there could very likely be one that gives a much better interpretation of the problem. Alright, so this is our function, and what would it look like for when n is prime, and then when n plus 1 is not prime. So if it was prime, floor of P over 1, floor of P over 2, we know that, let's see, floor of n over 1, floor of n over 2, floor of n over n, definitely seems like there would be an explicit construction for something like this. I think a combinatorial interpretation would be very helpful here, actually. I recall seeing something similar on Elmo. Can't remember exactly what the problem was. Something summing min of floor something, and then that's equal to another sum. Believe that there was some kind of multiplication table involved. So I'm thinking that combinatorial interpretation might be a good idea here, but not completely sure yet. It would be nice if it kind of, the expected value of the increase or decrease was always 0. That would be particularly nice since I would finish the problem. I guess I'll just compute a few terms to get something. Okay, so a sub 1, a sub 1 is obviously equal to 1. A sub 2 equals 1/2 times 2 plus 1, so 3/2. A3 equals 1/3 times 3 plus 1 plus 1. Is there a reason that it kind of looks like Fibonacci numbers, or that might just be a coincidence, but let me just verify that I did this last one right. Looks right, yeah. Alright, 1/4 times floor of, yeah, it's probably just a coincidence for the Fibonacci part. 4 plus 2 plus 1 plus 1, that would be 2. A4 equals 2, it seems to be. Okay, I suppose that's, actually I'm kind of getting Fibonacci number vibes again. A4 equals 8/4, that might be a coincidence, but let me just, computing A5 is, let's just check that. Floor 5/1 plus 4 5/2 plus 4 5/3 plus 4 5/4 plus 4 5/5. That would be 5 plus 2 plus 1 plus 1 plus 1. If I'm correct, that's, yeah, alright, 5 plus 2 plus 1 plus 1 plus 1, yeah, okay. Alright, so unfortunately no Fibonacci, 10/5 or 2, again. Just gonna keep them in fraction form just to see if there's anything. Alright, alright. Let's take a 6, 1/6 times 6 plus 3 plus 2 plus 3 more after that. So that would be 14 over 6. It seems like if I didn't make any errors. Okay, so 14 times 6. I don't know, I feel like there's something about the sequence floor of n over 1 plus 4 of n over 2 that has something I feel like I recognize, but it would be unlikely. What kind of sequence would that form? I feel like getting that sequence explicitly would be nice. Alright, let's try A7, I guess. A7 is 7 plus 3 plus 2 plus 4. Yes, okay. 7 plus 3 plus 2 plus 4, if I'm correct. And that would be 16 over 7. So again, the pattern with primes, I guess, is likely, oops, not A6. Patterns with the pattern with the prime number is increasing by 1 implies. It seems like it decreases at a prime number sometimes, and then increases at the next number, but sequence. Okay, prove that a sub n plus 1 is greater than a sub n infinitely often. This might actually be approachable by limits. The reason I say that is that a function that goes off to infinity if its if it's more linear, then it generally has to have infinitely many points where it's okay. So we're doing this over the integers, so there's no asymptotes at all. If I recall, there was a lemma, an increasing sequence of, or any sequence of numbers has a monotonic sequence. So any sequence of numbers mn plus 1 numbers, I think, has a monotonic sequence, monotonic subsequence of length n plus 1 or n plus 1, I think. I'm not completely sure, but it might motivate just a little bit. Anyways, so if a sub n plus 1 was greater than a sub n only finitely often, then it's obvious that it can't go off to infinity. At some point, it'll stop increasing, so it clearly can't go off to infinity. However, if we can show that it's unbounded, then we're done with part A. And that feels a lot more feasible. 1 over n times floor of n over 1 plus floor of n over 2 plus floor of n over 1. The reason it feels more feasible is because you might know that floor of that 1 plus 1 over 1 plus 1 over 2 plus 1 over n, that is proportional to log of n, i.e. we can, if essentially the limit 1 over 1 plus 1 over 2 plus 1 over n all over so essentially 1 over 1 plus 1 over 2 plus 1 over n is approximately log n times some constant. Anyways, if we could just get most of the divisors most of them to be okay. Actually, that might actually work. Since floor of n over 1 is greater than or equal to n over 2, floor of n over 2 is greater than or equal to n over 3. If I'm correct, this is floor of n over 1 for floor of n over k is greater than or equal to, it's greater than or equal to, so okay, floor of n over k plus 1 is equal to CL of n over k for most values. But anyways, if we consider a sub n plus 1, we can equivalently show that a sub n plus 1 is okay. So we want to show that a sub n plus 1 is unbounded. And we can do this as follows. I add 1 for the reason that if you add 1, then you're adding 1 to each term, which makes the entire thing greater than or equal to 1 over n times CL of n over x, because the inequality because of the inequality. Floor of n slash k plus 1 is greater than or equal to a ceil of n slash k. Oops. You can just verify this inequality holds. You just have to check it on integers since they're equal on non-integers, and that holds on integers anyway. That holds on integers for clearly. So, anyways, we end up with a number that's a sub n plus 1 is now greater than or equal to. So now a sub n plus 1 is greater than or equal to ceil of n over 1 plus ceil of n over 2 plus ceil of n over n all over n. But then that's also greater than or equal to n over 1 plus n over 2 plus n over n, since ceil of n over k is greater than or equal to n over k. And now we just cancel out the n. So we just need to show 1 plus 1 over 2 plus 1 over 2, 3 plus 1 over 4 plus is unbounded. And that's well known, actually. This is the harmonic series, so which anyways, so that solves part 1, part A. And since this is well known, if you want a quick proof, consider the terms less than or equal to 1 over 10. Greater than or equal to 1 over 10. They're all greater than or equal to 1 over 10, but there's at least 10 of them. So there are 10 of them. So you get that the entire sum is greater than or equal to 10 times 1 over 10 for that part. And then for the rest, you can do. There's going to be 90 numbers. 90 numbers after that, and then those are greater than or equal to 1 over 100. So that'd be 9/10, and then you get plus 9/10 again. Since you have 900 numbers, and we're talking about 1 over 1,000, so you get 1 plus 9/10 plus 9/10 plus 9/10, so on, and that goes to infinity, which is means it diverges. There are a lot of proofs for this, but it's well known, so that solves part 1, part 8, and now I would think that part B is probably the more difficult problem. A sub n plus 1 is less than a sub n infinitely often. That seems more difficult for sure, since as we saw before, it looks like it did not decrease very often at all. We had 1 goes to 3 halves increases, 5/3 increases, 8/4 increases, and then 10/5. It stays the same, but that means it doesn't decrease. 14/6 increases, and then we only got 1 decrease at 16/7. So we only have 1 decrease so far, which makes the problem slightly more for this part seemingly more difficult. But can we consider prime numbers to get this? Because I feel like prime numbers might help here. Okay, so 1 over n times floor of n over 1 plus floor of n over 2 plus floor of n over n. So it would, so having it decrease, we want, okay, so we're essentially adding in a floor, we're essentially adding in 1 over, we're definitely adding in at least 1 there, due to the floor of n over 1, when we add, then we're adding in about 1/2, so that's a kind of thing. When we add 1, it seems like we're getting to a point where it increases a lot, and it seems like it increases more than it decreases, so this is probably the more difficult part of the problem. Okay, so let's consider floor over n over 1 minus floor over n plus 1 over 1. We would want the entire thing to be negative, and how do we get that? Let's see, so 1 over n times 4 over n over 1 plus 1 over 4, okay. Can do a quick calculation in my head. Okay, okay, I guess that the one thing I would really just try is primes, since it kind of decreases more for primes. It seems like, anyways, so floor of p over 1 is floor of p over 2 plus dot dot dot, floor of p over p. For everything that's from 2 to p minus 1, that's p minus 2 numbers. Every one of those has a decrease of okay. Okay, I was thinking for a second that, one thing we could try is considering p slash p mod, why'd that give? Oh well. P mod, a prime q. We would want a prime such that p minus, so that p is going to be congruent to something large mod q, so that we get a bigger remainder. And how would this happen? So we can consider the primes dividing some, remember we can't take p minus 1, so p minus 2 but anyways, the reason that doesn't work is that even though you could think, oh, it's a remainder p minus 2, but in reality it just means that they're congruent, not necessarily that it's a remainder. So anyways, so floor of n over 1 plus floor over n over 2 plus dot dot. Definitely feels like there would be construction. It occurs not very often, so I don't think a density kind of argument would work. So it really feels like there's some sort of construction feel to it. Can we get this to happen at all, for it to decrease at all? So I'm going to actually compute more terms just to see. what kind of construction you might want to try. So I'll try it here. So A8 equals 8 plus 4 plus 2. 8 plus 4 plus 2 plus 2 plus 4. And that would be 20, I think. Yeah, 20 over 8. Is that a decrease? Does not seem to be so, since here we get 5 halves, definitely greater. Let's try 9 now. A sub 9. Let's see, so we would get A sub 9 is equal to 1 over 9, 4 over 9 over 1, 4 plus 4 over 9 over 2 plus 4 over 9 over 9. So that's 9 plus 4 plus 3. 9 plus 4 plus 3, and then that would be plus 2, 9 plus 4. Actually, plus 5. So okay, so I think it would be 23 over 9. I would think that might be a decrease. Nope, increase. Okay, so let's try A10. That's 10 plus times 10 plus 5 plus 3. That's over 18 plus 2, and then plus 6. No, 7. So 10 plus 5 plus 3. It's 18 plus 2, 20. So then plus 2. I think I probably computed A sub 9 wrong. I'm gonna check that again. It's 9 plus 4 plus, so that's 13 plus 3, 16 plus 2, 18 plus, and then we have from 5 to 9, so I think I computed it right actually. So now for 10 plus 5 plus 3, so we have 18 plus 2, 20 plus 2 again, that's 22, and then we have 5 more numbers, so it's 27 over 10. And still an increase, and let's see what happens for primes again. So A sub 11 equals 1 over 11 times, so 11 plus, okay, so 11 plus 5 plus 3, so you have 11 plus 5 plus 3. That's 19, then plus 2, 21, then plus 2, it's 23. Then we have from 6 to 11, that's 6. So I think 29. And it would be another decrease, so looks like primes seem to be a very possible candidate. For a given prime, let's see, so for a given prime, we have that the remainder is 4 of p over 1 plus 4 of p over 2. So I want some kind of bound on that. Okay, so 1 over n times 4 of n over 1 plus 4 of n over 2 plus 4 of n over n. Can we take some kind of okay, I'm kind of getting a Dirichlet feeling now, actually. What might have so what happened was I was thinking the entire thing kind of depends on p mod k for k less than or equal to p. And now I was thinking, okay, so p mod k, where have I seen that before? That's Dirichlet. So for a given number, a k, there are infinitely many primes that are, for example, k minus 1 mod k. In particular, there are sufficiently large primes greater than k. So p congruent to k minus 1 mod k. And that would give some kind of bound. Alright, I'm going to check it for 12 and 13 now. I want to see if the claim holds. If it does, it's probably directly computable, and I might leave you with the exercise of trying it. If you want to see how the solution it goes, I would probably visit the apps form. But I think I have a pretty good idea in my head of what it might look like. Okay, so 1 over 12 times 4 of 1 over 12 over 1 plus 12 over 2 plus dot dot dot. That, okay, I'm just going to quickly write it out. 12 plus 6 plus 4 plus 3 plus 2 plus 2. And then now we have from 7 to 12, so that's plus 6. 10, 13, 17, 23, 35. So 35/12. looks like it's greater than the previous one. Now we can check a sub 13 equals, so now let's take that 13 plus 13 plus 6 plus 13 over 3 is 4 plus 3 plus 2 plus 2 plus, then we have from 7 to 13, so that would be 7, 11, 12, 14, 18, 24, 37 looks like, 9, 11, 14, 18, 24, 37, 37 slash 13, looks like it decreased, yeah. So, looks like the idea for primes works. Let's see, if I can, I'm going to try and see if I can get the solution quickly. Okay, so, what we want to show is that p over p minus 1 is greater than or equal to floor of p over 1 plus floor of p over 2 plus floor of p over p all over floor of p minus 1 over 1 plus floor of p minus 1 over 2 plus there's probably a actually not too difficult bound for this, I would suppose, since floor of p over 1 plus floor of p over 2, that's greater than or equal to p over 1 plus p over 2 plus but we want an upper bound for it, if I'm correct. Wait, one upper bound for it? Yes. We want an upper bound for it. Okay, so to bound it above, okay, so we notice that p mod 1, p mod 2, p mod p, so essentially there are p minus 2 of them where the residues are at least 1, so we get something that goes to minus, so they're all less than or equal to, except for the first and last one, they're all less than or equal to that number minus 1 over denominator, if I'm correct. Yeah. So that would give, for sufficiently large p, it would be, or actually I don't really want to use sufficiently large here, but we would get we would get 1 over 1 plus 1 over 2 plus plus 1 over p minus p minus 1 over 2, or about So P gets large, that would erase the 1. So you get 1 over 1, 1 over 2 plus 1 over 3 plus dot 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 1 over P, then all divided by, in this case we want a lower bound. So for this, P minus 1, let's see, P minus 1 has P minus 1 over 1, P minus 1 over 2 plus dot dot. Okay, okay. P minus 1 over 1, P minus 1 over 2, dot dot dot. Doesn't seem like we actually need that strong of a lower bound. But essentially what happens is that the top, we have an additional, on the top we have the minus 1 essentially gives us extra room, and based on that, the prime, the calculation for primes works out. I believe that it works out, and that finishes part B. So what it means is that for primes, I think larger than at least 7, at least 7, or yeah, so for primes at least 7, the number for P minus 1 is going to decrease, is going to be greater than the number for P, or f of P minus 1 is greater than f of P for primes greater than or equal to 7. That's the main idea, I believe. So yeah, thanks for watching this video. Hopefully you like the content. If you want me to present a more thorough approach about this part, I can do it in another video, or I can just comment it down below. Anyways, thanks for watching. Hopefully this helped you.